Okay. I think. Okay, I think we can continue. So last time we still have something left. Okay. So we haven't yet. So the questions on this part is finding the internal force at point B. Okay. So point B is it's here, right? It's B here. But before we go to point B, we haven't yet finding the FVC here, because I think that will be important to know, and then from that force we can find the internal force here, right? I think we need to find all the force in the whole the diagram, and then to find the internal at B, later we are going to use those force and finding B. Okay, so first we need to find this. Okay, as I mentioned, and I think a few tips for solving statics is first start with the moment. If you remember statics course before, start with the moment. Okay? Because moment you will include everything, and then after that you can either find the force in the x-axis or the y-axis. Okay? So let's start with that. I already calculated the numbers, so I will give you the numbers. So first, let's calculate the sigma moment at A. Okay. Okay, because our goal first is finding the FDC. Okay, it's FDC here. Okay. So we are going to take the moment as 0 as usual, and then let's start with the I think 5,000 pounds, and then we rotate on A. So we rotate goes here, right? So this is clockwise, right? Clockwise means you need to take it as a negative sign. So negative 5,000, and what is the distance? Let me check the distance. The distance is 10.3. 10.3 is from the triangle. Okay. Triangle, the distance is, the base is 10, and from the resultant of the force, the distribution should be 1/3. Okay, 1/3. So 1/3 multiplied with 10 is 10/3. So this distance is 10/3 inch. Okay, or feet, right? Let me write there, and then 10/3 plus, okay, the other part, okay, because we are going to, our perspective is on A, right? So we go here and we find this FDC sine, right? Sine theta, and then it's going to counter, right? Counterclockwise, so that's why it's plus FDC sine theta. And what's the length? The length is from C to A is 10 and 2, 12. Okay, so let me go, let me make it, this is 10/3. Okay, and then from A to C, this is 12. Okay, so we are going to multiply with 12. So this will be FDC sine theta. Sine theta is here from the, we got from the triangle here. And let me give you the final results. Okay, you can also check if you want to calculate with your calculator. So FDC is 3610.5 pounds. Okay, since we have FDC, then we could work on the Fx and Fy. So sigma Fx equals 0. Then this will be, there is only
AX, right? So we could say this equal, let me write FDC cosine theta is equal AX, right? Okay, and then FDC is 3, 6, 10.5. Cos theta is 12/13, and this will be AX. So here AX means the reaction on A at pin A is spin, right? Yeah, at pin A. AX is 3333.25 pounds. And then the sigma Fy, this is AY plus the FDC sine theta, and then 5,000, right? 5,000 is opposite side, so negative. So AY, I will directly put the result. FDC the same, sine theta is 5/13, so this would be 3, 6, 12.5 lbs. Okay, so AY, AX, FDC, all we got together, right? Okay, so we get this, we get this, okay? So we got three results, okay? And now, okay, we need to find the internal forces on B, okay, which is around here, okay? This is B. Okay. So let me copy the original picture to make it clear. Okay. Copy, let me copy, maybe copy here. Okay. Oh, this is 5,000. Okay. Now, what we need is, we need to cut B open, right? We need to cut B. So we need to see what kind of force inside. So let me use green to give you some idea what will happen. So if we cut B, then what will happen here, the distribution of load here will also cut, and the shape is not the same triangle, right? It becomes this triangle that looks like a small triangle here. It's going to. So we are going to look on only this part now. Only this part. Okay. Okay. Now, what we are going to do? So if we are, let me write and draw a little bit bigger so that you can see clearly. Okay, so let's say this is AB. Okay, this is 6 inch. Okay, and this is the, so we say this is almost a triangle that's cut off, right? And this is the distributions loads. Okay. Okay, now the way we are going to do this part is by, let's take this, okay, let's take this, and you can see that we can have two shapes, okay? A rectangle and a triangle. I think we can use that, okay, to formulate our loads. Okay. So before that, let me complete the picture. Okay. So from the free body diagram, when we talking about this, we know AX,
we know AY and we know the FDC. So let's at least write the AX into A. Okay, let's write AX and AY. Okay, so maybe here is this is AX is 3333, so let me write 3333.25, and there will be, it's going up there, this is 3612.5. Okay, now how to make sure what's this value, and what's this value, okay, any idea how to find this value, so that we can, for example, we can multiply the area, the rectangle, the base and the height, the base and the height. The base width is the distance, and the height, we can assume the height is the force, okay, the force itself. So how do we know what was the value here? Any idea? We need to have some good observation in geometry analysis. So if we look here, we have a triangle, right? And I think we can use the ratio, okay, 6:4, okay, and we know this part here. Okay. Let me give you an idea. Okay, this whole distribution load is 1,000 per distance, right? And where is the highest value for the load? It's not distributed evenly, right? Where's the highest value? Here, right? So do you agree that this part here, the highest value is 1,000? Agree, right? Okay. So we could imagine this triangle. Okay, it's not really straight. Let me clear this. Okay, now it's okay. So this is 1,000. Okay, and then this is 6. This is 4, and let's say this is y. Okay, so we could use a triangle ratio. 1,000 divided 10 is equal y over 4, right? So y is, so this is cancel, y is 400. Okay, so we get 400. So this is 400. Okay, this is 400, and this is the same height, 400. Okay, so we could take 400 multiplied by 6 for the rectangle, and another one will be 600, right? And multiply the distance and using the triangle area, right? Okay. So we could approach this with geometry, so we can remember the loads and distributions load. Okay. So we take the load here being so this one is 400, same here, 400, okay, and this one here becomes 600, okay, and this triangle, let's say the area is 600, or maybe it will be confusing if I say area. Let me say the resultant force, okay, or resultant loads. So 600 multiplied by half, or maybe half 600, and then what, 6, right? So 3 by 600 is 18. Okay. And for the rectangle, the loads is 400 by 6. Let me use this. It's 224, right? Okay, before we using these loads and using the loads for calculating the moment, what we need to find is this. So this is the end. This will be the shear, and this will be the moment, right? Okay, according to what we find, I think we could conclude the n is 3000, right? So we could, because the sigma fx equals 0, okay, that's the key, right, for statics. So n is 3333.25 pounds. And then for the sigma fy, okay, sigma fy, let's say this is positive, okay, this, okay, and then the loads, those two, one 1800 and 2400, we can total 4000, right? 4000. So this will be total 4200. So we can use this 36 minus and minus the V, and V or shear is, you can calculate this, just subtract both of them. Okay, so we get this and this. Okay, now before I forget, we need to put 1800 and 2400 in a good place. Okay. So remember, the triangle is 1/3. The rectangle is 1/2 in the middle. So the triangle, okay, is going to be 1/3. So 1/3 of 6 is 2. So this will be maybe here. Okay. So there will be, it's going down here, 1800, and this will be 2, right? And then what else? The 2400. 2400 is at the middle. It's around here. So this will be 2, 4. Okay, I forgot to mention this. So this will be so 2 inch. So this is 1, right? 2, 1, 3, right? So 6. Okay. Let me wait for a while so that you can process this first. Okay, this is a little bit complicated because I think the way you see these problems, we cannot really compute what happened in this B, okay? Because we still have unknown force in the environment. So that's why on the previous process, we need to find that first. We need to find here, we need to find the reaction on A. Because this reaction A and the force in this pin, okay, this will be affecting what happened inside B. Okay? So that's why we need to find the reaction here, and the reaction here, and then we can find the result in B. And the twist on the question is really if the distribution loads is maybe just one resultant, maybe you can see I think more clear. But because we have this loads here with distribution, then we need to make this distribution solve first. So we need to solve this and make it into one single force. And if you remember statics, to solve the loads, the distribution loads, you need to use the area. Okay? If that is a rectangle, and if that is a triangle, what's happened, okay? And what's happened with the distance on the resultant force. Okay? So when this is the triangle like this, it's supposed to be at the 1/3 of the distance. Okay? Okay? And then, because on this process here, we cut this, okay? And we move into here. We name all the numbers that we get before. Okay? We rename, and then we have another distribution. Okay? That is cut. Okay? It's cut. And then we can try to approach these loads by making it into two shapes. It's triangle and then rectangle. Both have different distance for the force. Okay? The distance for the triangle, again same, is 1/3, but 1/3 from 6. That's 2. Okay? So that's why when we approach the area, then this 1,800 is in 2 inch here. Okay? And then the rectangle, we get the area as 406. So 2,400. And where? It's half of 6, which is 3 inch. So 2, 1, 3, so it's here. Okay? Okay. Now we also can compute all the things here. Okay, so N and the shear. Okay, N and the shear. And we might need that for solving the moment at B. Okay? The moment at B. So okay, I think we can try that out. So the moment, sigma moment, let me, I hope you don't mind, I'll write a little bit up here. So let me write here. So sigma moment at B, okay, is equal to 0. Okay, sigma moment at B equals 0. So we could take this part here and twisting over there, okay, with the distance 6. Okay. So it's clockwise. But I think clockwise or counterclockwise, if you mix up, but as long as you're consistent, whenever you find counter is negative, and whenever you find clock is negative, whenever you find the counter is positive, I think it should be okay, right? Okay. And multiply with 6, and then this 1 goes here. 1 plus 3 is 4, so it's now positive.
So clockwise and then counterclockwise. And then one more is 2400 is the same, positive. And now it's 3. Okay. And then plus m. Okay, plus m.
The one that we are looking for at B. Okay, this one. Okay. So all the forces, they are affecting the moment, right? And of course, this is the moment that we are going to find.
And the moment at B is equal from here. This is equal to 0. After you calculate, you can also check. This is around 7.75 feet LPS. Usually in the standard unit,
Should be Newton meter. So I hope you don't mind. I'm using another standard here.
I will try to look on more examples that look using the standard version. So for
I think for the first week and maybe next week, still a little bit, we're still talking about standards. We're still talking about standards. Especially maybe review something that we might miss.
So the answer is this. The answer is N, okay, and the shear and the moment. Okay.
So these three are the one that we are looking for. The original question is what is the internal force on B? So we need to find those three. The question is asking the internal force. Okay. When we finish dealing with this statics review, I think next week, I will maybe a little bit moment review a little bit more, and then we switch to the new chapter, and we focus on the first one is going to be the normal stress or the stress.
Okay, now if you don't mind, okay. I think if you need, maybe you can take picture first. Okay. Okay, the next one is still one more example for this review. Okay, I took from the textbook. So the question is long, but let me give you the picture first, and let me describe first what this picture means. So we have a bucket truck in the figure.
So of course it has all the details, okay, the distance, okay, all the like the angle here, okay, for this triangle, okay. And then another angle, the distance, and a person. So he's supposed to maybe working something on that. But the questions, okay, the questions.
Let me give this. Okay, so electrical worker stands in the
Bucket that hangs from a pin at ND of the boom of, we said, cherry picker, the weight of the worker and the bucket is this, okay, 1,335. Between A and C, the weight is this. Okay, so it's along the distance. Okay, so if you need to find the exact weight, you need to multiply with the distance. Okay, what the distance? Okay, and between C and D is 140 Newton per meter. Okay, assume AC and AD uniform beams, which means that the distribution is even distributions. Okay. Okay, determine normal force, transverse shear force, and bending moment. It's the same question as before. We need to find what? This is N, this is V, this is M. Okay. So this is N, V, and M that act at cross section E in the midway of A and B. So we need to find. So let me just give you idea that this will be total weight is 1,335 Newton. Okay, and then we need to find this from this E. Okay, so we need to cut open E. So the same procedure as before, but just different schematic diagrams, but the same as before. So we need to find all the environment reactions first, or probably we build a free body diagram, find all the forces, external force, okay, and then after that we cut open this E and find the internal force. But before that, let me complete with the weight. So let me write the weight AC. AC is 200 Newton per meter, and if you see, AC is 0.2, 0.2, and 1. So it's 1.4 total. So we could take the weight is 200 Newton per meter multiplied with 1.4 meter. So we get 280 Newton. And where should I put 280 Newton? Because it says in the questions, it distributed uniformly, right? Evenly distributed, and we can assume that the beams is uniform, so we could put in the middle. Okay? So this weight here. Okay. So the weight is on the middle. So this is 1.4. So we need to put on 0.8. So maybe around here. So this is. Okay. Okay. And then the other weight is WCD. WCD is 140 Newton per meter multiplied with 1.2 meter. It's going to be 168 Newton. And then the same, we need to put at the middle of this 1.2, so this will be maybe around here. Okay. Okay, and I think
I think we need to maybe just cut this open and make a free body diagram on this part, right? I think we can do that. Okay, we can make the free body diagram. Let me do in here. Okay. Let me make a little bit smaller. So let me just work on that. This is the weight. This is the 168. Okay, and then let me name first D, C, and B, and A. Okay. E is in between A and B, but let me just write the big one first. All the name. So B is here. I think this is the 218 Newton, and B is actually a connector pin here. Okay, connector pin. So it goes to be. So it has some reactions here, right? So if we imagine it's moving, so we can make it like an external force as also on this diagram. So we make that as a force. So on B is, let's say, here. So on B we have a force, okay, with a angle 60 degree. Okay, and then we have, if this is A here, okay, let's say A is going to be there, okay. So I assume A is going over there because we have weight that goes down, okay. But because this body diagram is on diagonal, okay. So let's make this diagonal in terms of so we looking at this diagram like here. So this will be and the axis. Okay? So let's make this the beam as its axis. Okay? So we could take the A, and make it into, like, this is the AX, okay, and this will be the AY. Okay, and then let me erase first the resultant here, okay, to make it clear. Okay. So, and before we end the class, so all the component here we need to multiply with the angle, okay? And then using this, okay, like previous example, we find this first, okay, and then we cut open here, or E is in between A and B, okay? And then we find the normal, we find the shear, we find the moment. It's pretty much similar. I think the principle is, I think, okay, but the more the question have, it's kind of, you will get more complicated because of the, for example, like this one, there are many numbers, but you need to keep the principle first. Okay? You need to keep the principle first. What the first thing you need to do? Okay. So every time we have this kind of question, I think in all the chapter in our mechanics of materials, okay, sometimes the questions they give like really a lot of information. Okay? But you need to keep in mind what we are going to find, what we need to do. Okay. So as we mentioned in the previous example,
we need to open this E, right? We need to find the normal here, the V, and then the moment in the bending moment. Okay? But to find that, we need to find all the external force that works on the diagram. So that we need to find the whole body diagram, find the forces, and then cut open, find the internal forces. Okay, that's the steps. Okay. So I think we are going to solve this next week, and we can continue to normal stress. Okay. So I hope this review for statics. I think maybe you can also review with your previous notes. Okay, if you still have the notes. So yeah, I think that's all. And maybe to also to help, I will give maybe 2 or 3 exercises you can take on. Okay? And maybe week after that, maybe I'll just give you my notes, okay, for that one. Okay, and we